Hey everyone, my name is Saarik Kalia and I'm a PhD student at Stanford, and I'm going to be telling you about recent work with Will DeRocco and Peter Graham on the importance of thermal effects in axion inflation models. The axion is a popular candidate for the inflaton, and most such models operate under the cold, slow roll paradigm. This means that the universe is just dominated by some inflaton condensate, which is constant throughout space and slowly evolving through time. But there's no messy particles flying around or anything. However, generically, axions can couple to other gauge sectors, and these couplings can significantly complicate the situation. They can allow for the production of particles and even the generation of the thermal bath and for thermal effects to come into play. The punchline of our work is that even small such couplings will actually cause these thermal effects to become important and turn what you thought was a cold inflation model warm. The rough outline of my talk will be as follows. First, I'll go through some of the basics of warm inflation and introduce the particular model we're going to be working on, and in particular show how dissipative effects can source a thermal bath at some equilibrium temperature. Next, I'll show that this equilibrium is actually an attractor solution that will be reached regardless of initial conditions. So if you start with some bath at a different temperature, you'll reach the equilibrium temperature. And we even show that if you start in a vacuum, we find it suggestive that you will still reach this thermal equilibrium. Finally, I'll actually show that the presence of this thermal bath is quite important. It can affect both the predictions and the dynamics of inflation. And I'll actually map out parameter space and show you that for large parts of parameter space, this bath is actually important. So without further ado, let's get started. So this is the scalar equation of motion in inflation. It looks like a usual equation of motion for a scalar, except it has this additional term, which is often called Hubble friction. And this basically just acts to slow the inflaton down as it rolls down its potential. And the size of this Hubble friction is just determined by the usual Friedmann equation based on the energy density of the universe. However, if there's a thermal bath around, then an additional effect comes into play, which is known as thermal friction. Just like Hubble friction, this also causes the inflaton to be slowed down. And the amplitude of this effect is related to the temperature of the thermal bath. In particular, there's also an additional effect, which is that the dissipation itself also acts to source the thermal bath. So the thermal bath is both gains energy from the dissipation of the inflaton's kinetic energy, but it's also has some of its energy redshifted away by the usual Hubble flow. And so it'll stay at some equilibrium temperature as time goes on. And as the inflaton continues to roll down its potential, and the potential gets steeper and steeper, this temperature can get larger and larger. And as you can see, actually, as you go on, this temperature can become quite large and actually become important. So this is the particular Lagrangian we're going to be working with. We have some axion inflaton, some gauge sector that it couples to, some non-abelian gauge sector, and some potential that the axion rolls down, and then some coupling between the axion and the non-abelian gauge sector. In particular, it comes with this axion decay constant, which determines its strength. So larger Fs mean more weakly coupled, and smaller Fs mean more strongly coupled. Importantly, because of the shift symmetry of the axion, the potential receives no thermal corrections. The only effect is precisely the effect I showed you on the previous slide, which is this thermal friction. And as you can see here, it roughly scales as T cubed over F squared. So the hotter the bath is, the more friction there is, but also the more strongly coupled the bath is, the more thermal friction there is as well. Now, this is all what the situation looks like for a pure SUN gauge sector. However, the story changes a little bit when you add in like fermions. It actually turns out if you add in fermions, which are much lighter than the temperature of the bath, then the thermal friction effect will get suppressed by roughly m squared over t squared. Okay, so I told you that this equilibrium exists, but how often do you actually reach it? Well, it actually turns out that this equilibrium is an attractor solution. So if you begin in a thermal bath, whether you're hotter or colder than the equilibrium temperature, you will eventually reach it. In particular, if you begin above the equilibrium temperature, then you'll simply just redshift down to it in a few e-folds. If you begin below the equilibrium temperature, However, it was shown in recent work by Kim Berghaus, Peter Graham, and David Kaplan that thermal friction will cause the bath to heat up, and you'll actually reach the equilibrium temperature within Hubble time, just so long as you began roughly above Hubble for your temperature. So that's all if you begin in a thermal bath. But actually, even if you begin in a vacuum, we show that it is at least suggestive that you will still source this thermal bath. This is due to an effect described by Anber and Sorbo a decade or so ago, where a rolling inflaton with precisely the same type of coupling that we're working with can cause the exponential production of gauge bosons. And in a non-abelian case, this production will continue until nonlinearities and self-interactions start to become important in the equations of motion. And we show in our work that actually you can easily generate an energy density above Hubble to the fourth before these self-interactions take over. Now, once they start to take over, we can't exactly say what specifically happens. However, based on entropic grounds, we believe it's likely that they will just thermalize. And if that is the case, then you can see that the temperature that they would result in would be above Hubble, and then so the previous case would apply. So while we can't say for sure what exactly happens in the vacuum case, we think it's very suggestive that even in the vacuum case, you will still source this thermal bath at this equilibrium temperature. Okay, so I've told you there exists this bath and you will reach it, but what does it actually do? What are the important effects of this bath? And so there are a few quantities of interest we're going to look at to try to determine that. The first is going to be the ratio between the thermal friction and the Hubble friction. We call this Q. And this basically just tells you whether the dynamics are dominated by Hubble or by the bath. This just compares the warm inflation dynamics to the cold inflation dynamics. Next, we're going to compare the temperature of the bath to Hubble. And this basically just tells you whether the fluctuations of the inflaton are set by thermal effects or by quantum effects. Or in other words, whether the C and B predictions like AS, NS, R, et cetera, are going to be dominated by warm inflation or cold inflation. And then finally, we also check whether Hubble or the temperature is above the axion decay constant, because this sets the upper cutoff of our EFT. And so if either Hubble or the temperature are above this value, then the effective field theory will break down entirely. And so this is no longer an accurate description of the axion. So based on these, we classify our parameter space into a few different regimes. We have the strong warm inflation regime, where both predictions and dynamics are dominated by warm inflation. We have the weak warm regime, where only predictions are dominated by warm inflation. We have the cold inflation regime, where neither predictions nor dynamics are dominated by warm inflation. And then we also have a couple broken regimes. And we break this up into this naively broken regime, where even a cold inflation theorist would expect the EFT to be broken because the Hubble scale is above F. But we also have this thermally broken regime, where Hubble is below F, but the temperature is above F. So a cold inflation theorist might think that they were safe, when in fact thermal effects will break the EFT. And for our purposes, all of these quantities are just going to be evaluated at some fixed number of E-folds before inflation, in particular 60. So this is an example of what parameter space sort of looks like in our model. I've taken some particular potential, monodromy potential, but we find that our results are relatively generic regardless of the potential you take. And on the vertical axis here, we have the axion decay constant. So higher up means weakly coupled, lower down means strongly coupled. And on the vertical axis, horizontal axis, we have the scale of the potential, which you can think of as a proxy for Hubble. And again, I'm showing the regimes that I talked about on the previous slide. So where both predictions and dynamics are dominated by warm inflation, where just predictions are dominated by it, and where neither are dominated by it, as well as the naively broken regime and this new thermally broken regime. Also in green, we show the normalization, which would be required to match CMB, observed CMB amplitudes in the cold inflation paradigm. And so you can see here that a naive cold inflation theorist might have thought that anywhere down to couplings of 10 to the 13 GeV would be totally safe before you would have to be concerned about your EFT breaking. Whereas we actually find that even couplings as high as 10 to the 15 GeV can be dangerous, either because thermal effects will come into play or because the EFT will be broken. So you see, you have to be really within like 3 orders of magnitude of the Planck scale in order to avoid any thermal effects. And this is an example of a similar scenario, except for the standard coupling to the standard model rather than coupling to a pure SU3 gauge group. And so in this case, the presence of the up and down quarks are light fermions, which suppress the thermal effects as I mentioned before. And you can see now that the cold inflation regime extends much further down because the thermal effects are much weaker. We've also allowed here for temperature dependence of both alpha and the number of degrees of freedom. And so this leads to an additional effect where at low enough temperatures, the theory can actually confine as the coupling becomes strong enough. And again, we show the same C and D amplitude here. You see now the green line lies entirely in either the cold or broken regimes. So in this case, the properties at the observed C and D amplitude are not affected by the warm inflation at all. So in summary, I showed that dissipative effects can generate a thermal bath during inflation. I showed that the bath that they generate is actually an attractive solution. So you get to it regardless of the initial conditions you started. I've shown that this bath can be large enough that it actually changes your predictions and dynamics, even for quite small couplings. You need to be within 3 orders of magnitude of the Planck scale in order to avoid any thermal effects. So our work serves as a public service announcement that thermal effects must be accounted for when building inflation.